In this presentation, I'm going to find the equation of the projective line that joins the two projective points with coordinates 1, 2, 3 and coordinates 4, 5, 6. In projective geometry, every point is on a line with coordinates 0, 0, 0. Also in projective geometry, the point with the coordinates 1, 2, 3 and the point with coordinates 3, 6, 9 refer to the same point. Coordinates 3, 6, 9 is a scaled up instance of 1, 2, 3. So too is coordinates 15, 30 and 45. For the case of coordinates 1, 2, 3 and coordinates 3, 6, 9, the scale is 9 divided by 3. I'm using 9 from these coordinates and dividing by 3 in these coordinates to get 3. This gives me a scalar. I multiply this scalar by the coordinates 1, 2, 3 and I get the coordinates 3, 6, 9. And this shows that these 2 points are linearly related, and in projective geometry they are considered to be the same point. Now for our work on the points with coordinates 1, 2, 3 and coordinates 4, 5 and 6, it is vital that we check to see that these 2 coordinates in fact refer to the same point. I'm going to pluck a scale. 6 divided by 3 gives me 2. I could have picked 5 divided by 2 or 4 divided by 1. Just something to see could I find a linear scale. So using 2, multiply the coordinates 1, 2, 3 by 2 gives me 2, 4, 6. That does not equal the coordinates 4, 5, 6. Therefore, these 2 points are distinct points in terms of projective geometry, and we can proceed with our work. In projective geometry, the equation of a line is what we might call in old money in Euclidean geometry the equation of a plane. To find the equation of a plane, we need to know or to be able to find 3 distinct points in the plane plus a vector normal to the plane. But we only have the points with coordinates 1, 2, 3 and 4, 5, 6. Where do we get a third point from? Well, from earlier, every point in projective geometry is on a line to the point with coordinates 0, 0, 0. If our 2 points, these 2 points here, are on the plane, so too must be 0, 0, 0. We also require a vector that is normal to this plane, and we're going to use this as like a slope for our plane. I've sketched our plane here, and I have written in point O, 0, which is 0, 0, 0, point P, which is coordinates 1, 2, 3, and point Q with coordinates 4, 5 and 6, and I've sketched in a vector n that's normal to the plane, and that's what this little symbol here means, that it's orthogonal, it's 90 degrees to the plane. Now for our work, any vector that is normal to the plane will do. Okay, now that we have our 3 points located in the plane, we're going to use them to find 2 vectors. I found vector P to Q, working from the coordinates of the coordinates of P and Q. I subtracted point P from Q to get the vector P to Q. And this gives me, when I subtract, like for example, 4 minus 1 gives me 3, 5 minus 2 gives me 3, 6 minus 3 from 6 minus 3 gives me 3. These gives me the components of this vector PQ. And likewise with vector PO, I subtract the coordinates 1, 2, 3 from 0, 0, 0 to give me this vector PO, and components of that vector are minus 1, minus 2 and minus 3. Now how do we find this normal vector n that is normal to the plane? Well, if n is normal to the 2 vectors PQ and PO in the plane, then n is also normal to the plane. We're going to use the cross product to find a vector that is normal to vector PQ and vector PO. PQ cross PO equals n, a normal vector. PQ cross PO can be found from the determinant of the 3 by 3 matrix with rows, the standard basis vectors, that is I, j and k, and the components of vectors pq and vector po. So I have my 3 by 3 matrix here. The top row is the standard basis vectors I, j, k. The second row are the components of PQ, and the third row are the components of PO. And these straight lines to the side they indicate that we're taking the determinant of this 3 by 3 matrix. Now the technique I'm going to use to find the determinant is the basket weave technique. There are other methods to do that all give the same answer. They all give the answer of PQ cross PO. In the basket weave technique, we copy our columns I and j. There's our columns I and j, and we place it to the right of the vector of this 3 by 3 matrix. Now we end up with a 5 column 3 row matrix. And the basket weave technique is that we're going to mark out the down diagonals, and I've marked the down diagonals in green here and the up diagonals in red. What we're going to do is we're going to add the product of the down diagonals and subtract the product of the up diagonals. The down diagonals, as in green here, it's I 3 minus 3 gives me minus 9i. J 3 by minus 1 gives me minus 3j. K by 3 by minus 2 gives me minus 6k. And then on red, the up diagonals, minus 1 by 3 by k gives me minus 3k. Minus 2 by 3 by I gives me minus 6i. Minus 3 by j gives me minus ij. So I add the down and subtract the ups, and this gives me the PQ cross PO equals the normal vector, and I see where it's minus 9i minus 9i minus 6i gives me minus 3i. So I end up with the normal vector is minus 3i plus 6j minus 3k. The Cartesian equation of the plane is given in the form of a into x minus x naught plus b into y minus y naught plus c into z minus z naught equals naught, where a, b, c are the components of the normal vector. The normal vector n is equal to ai plus bj plus ck. In reference to the normal vector we found up here, minus 3 is a, plus 6 is b, and minus 3 is c. And in the Cartesian equation, x naught, y naught, and z naught is any known point on the plane. Compare this format with the equation of a line in the xy plane, that is y minus y naught is equal to m times x minus x naught. In the two forms, the MABC provides slope information. Now I'm going to choose for our point P, the coordinates 1, 2, 3, and plug those in for x naught, y naught, z naught, and A is minus 3, B is 6, and C is minus 3. Do a bit of plugging and chugging here, and I come out with minus 3x plus 6y minus 3z equals 0. I'm saying that that is the equation of the plane in Euclidean geometry, and in projective geometry that is the equation of the projective line connecting the projective points 1, 2, 3 with the points with coordinates 4, 5, 6. Now just going to check work to see if those points P, Q, O actually satisfy the equation, that we haven't made a boo-boo along the way. So plugging in the points for P with coordinates 1, 2, 3 into the above equation here, a bit of plug and chug, and I end up with 0. So this is in fact, that is on that point, coordinates 1, 2, 3 is on our plane, or the projective point 1, 2, 3 is on the projective equation for the line. Point Q, which 4, 5, 6, plug in, we also end up with 0, which shows, yes, that this projective point is on the projective equation of the line connecting them. And lastly, plugging in 0, 0, 0 gives me in fact 0. So I'm satisfied that this equation is in Euclidean geometry terms is the equation for the plane, and in projective geometry terms this is the equation of the projective line connecting the projective points P and Q. Thank you for watching, and I hope you found that helpful.